Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is Euler's formula for planar graphs, or Euler's polyhedral formula. So here's an example of a simple planar graph. It's a graph, which means that there's a bunch of vertices, these nodes, and there's some edges. An edge is a connection between two vertices. This is a simple graph because it does not have, as it stands, any double edges or loops. And it's planar graph because you can draw it in the plane without any edges crossing. There are 8 vertices, 10 edges, and there are 4 regions. So for example, the inside of that square is a region, the inside of that parallelogram is a second region, the inside of that triangle is a third region, and a fourth region is the outside region. So there are 4 regions. I could have drawn the same graph in a more complicated way, in a way that the edges do cross. That doesn't make this graph a not planar graph. This graph continues to be a planar graph because a planar graph is one that can be drawn in the plane without the edges crossing. In a planar drawing of a simple connected planar graph, connected means that there's just one connected component. You can go from any vertex to any other vertex via the edges. In such a thing, the number of vertices minus the number of edges plus the number of regions is 2. And this is Euler's formula. No matter what simple connected planar graph you have, and if you draw it as a planar drawing with no edges crossing, then there's an invariant. The number of vertices minus the number of edges plus the number of regions is 2. And one quick proof, which I gave in the other video, is a proof by induction on the number of cycles. If the number of cycles is 0, then you have a tree. And for a tree, the number of edges is 1 less than the number of vertices. So when you take v minus e, you always get 1. And the number of regions is 1. So 1 plus 1 will be 2. So for a tree, this is true. And if you don't have a tree, you have a cycle, you take one of the edges of one of the cycles out. And the effect of that is that the number of regions comes down and the number of edges comes down. And the number of vertices doesn't change. So this v minus e plus r of that graph doesn't change by taking that edge out. You keep doing that until you get to a tree. And because v minus e plus r was true for a tree, it will continue to be true for any such graph. I will give a different proof of the same Euler's formula, which is the subject of this lecture, later on for a slightly more general version of it. I said this was true about simple planar graphs, but if you think about it a second, if it's true for simple planar graphs, it's also true for general graphs. Because if you add a loop or a double edge, all you're doing is you're adding an edge and you're adding a region, because a loop adds a new region for you, as does a double edge. And so the e goes up by 1 and the r goes up by 1, but v minus e plus r does not change. So if you believe this theorem for simple graphs, you should also believe it for general graphs, although for connected ones. In this lecture, we'll also talk about what happens if the graph is not connected. I'm going to repeat myself. A planar graph is a graph that can be drawn in the plane with no edges crossing. So for example, this was an example of a planar graph. The drawing of a graph where no edges are crossing is called a planar drawing of the graph. Again, a planar graph is one where you can draw it without edges crossing, not that you must draw it with the edges not crossing. A planar drawing of the graph partitions the plane into regions. What are regions? Regions are the connected components of the complement of the graph in R2. You can talk about regions only if you have a planar drawing of a graph. A cycle is when you start with a vertex and you go through one edge to another vertex, and so forth, and you come back all the way where you started with no repeated edges or vertices. A cycle is planar because you can just draw it going around. In topology, the theorem called the Jordan curve theorem says that a plane drawing of cycle always divide their plane into 2 regions. This intuitively seems obvious for finite cycles, which is the thing that we're interested in graph theory most often. This is not hard to prove, but in topology, one gets to prove this for not just finite cycles, but infinite cycles, but also for just any non-intersecting curve. And the proof in that case is not that easy. And one reason is that a plain drawing of a cycle can be complicated, like this one here. In this lecture, we want actually a generalization of planar graphs. First of all, we want to allow non-connected graphs, graphs with different connected components, but we also want to allow some other things. We give this the name squiggle. So a squiggle is a plain drawing of a general graph, and it's a general graph, so I'm allowing loops and double edges. But we allow a finite number of loops without vertices. So now this is not really a graph because I'm allowing loops that do not have vertices. So it's possible, for example, for a squiggle not to have any vertices at all, to just be a bunch of loops without vertices. So this is a generalization of a planar drawing of a general graph. Another way of defining this is that a squiggle is a finite collection of vertices and edges such that if two edges cross, then there's a vertex at the crossing, and if an edge has an endpoint, then there's a vertex at an endpoint. There's no edges sort of hanging out there without a vertex at the other end of them. I learned this concept from my thesis advisor, Marty Isaacs. Let me give you some examples of squiggles. So here's one, just a loop without any vertices, but I could have one vertex, or I could have two loops without vertices and a vertex inside, or I could have this other shape. So these are all examples of squiggles. Any planar drawing of a general planar graph, connected or not, is also a squiggle. So this whole thing, for example, is one squiggle. For any squiggle, nil v is going to be the number of vertices, e is going to be the number of edges, r is going to be the number of regions, and c is going to be the number of connected components of vertices. And what's a connected component of vertices? It's a maximal cluster of vertices connected by edges. Because we might have edges that have no vertices on it, this is not the same as the connected components of the graph, because if there are some loops just hanging out there, we're not going to count them among C at all. Now, if a squiggle is a general graph, then the C is the number of connected components. So the question is is there a relationship between V, E, R, and C? What is it, and why is it true? So I urge you to stop the video, to look at a whole bunch of examples of squiggles, and try to see if you can guess what the relationship between V, E, R, and C are. Let's just look at some examples together. In this case, there's no vertices. V is 0. There's only one edge. There's just one loop. There's two regions, the inside and the outside. And the number of connected components of vertices is 0. Here's another example. The vertices is 1, E is 1, R is 2, and C is 1. Here's another example. V is 1 again. E is 2. The number of regions is 3 here. And the number of connected components of the vertices is 1. Final example, I have two vertices. I have 5 edges. I have the loop on top, and then I have these two other loops here, 3, and these two double edges. So that makes 5 edges. There are 5 regions inside the circle, inside these other 2 loops, inside this double edge. That's 4, and then the outside region. And the number of connected components of vertices is 1, because there's 2 vertices, and you can get from one to the other via edges. So again, stop the video and try to come up with the relationship between V, E, R, and C. If you do that, you will see that always the number of vertices minus the number of edges plus the number of regions minus the number of connected components of the vertices is always 1. This V minus E plus R minus C is an invariant of squiggles. No matter what squiggle you draw, V minus E plus R minus C will be 1. And our purpose is to see why that's true and see some examples of that. In a future video, we'll see some applications of this. So let's just check it for this general planar graph. Here, there's 12 vertices. The number of edges is 16. The number of regions is 8. And the number of connected components of vertices is 3. In this case, also, V minus E plus R minus C equals 1, as expected. Our theorem is that if you have any squiggle, then V minus E plus R minus C equals 1. If you have a connected general planar graph, then C will be 1, and you can take that C over to the other side, and you get V minus E plus R equals 2. But why is this true? And so our strategy is going to be this. We're going to consider this V minus E plus R minus C and call it M. We want to prove that M is 1, but the way we were going to prove that is to show that it doesn't change when you take an edge out. We also will show that M is 1 if a squiggle has no edges. So you start with your squiggle, keep taking edges out, M doesn't change. Eventually, you'll get to a squiggle with no edges. In that case, M is 1, and then you're done. Our first question is, what is M for a squiggle with no edges? Well, we have n vertices. N might be 0, by the way, and no edges. The number of vertices is n. The number of edges is 0. The number of regions is 1, because there's just one region, the outside region. And the number of connected components of vertices is n. And if you check that, check what M is, V minus E plus R minus C, you get n minus 0 plus 1 minus n, and that's 1, and that checks as predicted. So at least in this case, we're good. Now, for the general case, we're starting with a general squiggle. We already know that if there were no edges, we're done. Otherwise, if there are edges, then we take one out, and we show that M does not change. And we keep taking edges out, and M keeps not changing, and eventually we get to the squiggle with no edges, and for that we know that M is 1. And so M must have been 1 all along, because no matter what it was at the beginning, it never changed, and we got to where the m was 1. Start with a squiggle and take an edge out. It remains to show that m does not change. If I do that, the proof will be complete. So first of all, the number of vertices stays the same. You didn't take a vertex out, you just took an edge out. So the number of vertices stays the same, and that has no effect on m. The number of edges has gone down by 1 because you took an edge out. And so m at this point has increased by 1 because remember, we were subtracting the number of edges, and if you make E1 less, then m is going up by 1. So at this time, we think m went by 1, and we're a little bit worried because we want to show that m actually does not change when you take an edge out. Now, the question is that what happens to the number of regions when you take an edge out? Two things could happen. It could be that R stays the same. It could be that the two sides of the edge were already in the same region. And when you took that edge out, no new region was created. Or it could be that the number of regions went down by 1. It could be that the two sides of the region were not connected before, and by taking this edge out, now they are connected, and so there's one less region. If R stays the same, what happens to C? If R stays the same, my claim is that C goes up by 1. Let's say that this is our edge, the edge that we're taking out. If the number of regions stays the same, then what does that mean? Then that means that the one side of the edge and the other side of the edge were both in the same region. So imagine that you're sitting on a boat very close to this edge on one side. You should be able to go all the way very close to the other side without crossing any edges. If that's the case, then this vertex here and any other vertices that's connected to, there might be a whole bunch of vertices that is connected to it here. Those set of vertices, when you take this edge out, are going to be disconnected from the vertices on this other side. And so the number of connected components of vertices goes up if that happens. If R stayed the same and C increased by 1, then the combined effect of R and C is that M goes down by 1. But R could go down by 1. And what happens then? Then C stays the same. And why is that? So again, we have this edge. And when you took it out, the number of regions went down by 1. That means that the region on one side of the edge and the region on the other side of the edge were different regions. And so what that means is that if you were on a boat here, you could not have made your way all the way here. And the reason for that must have been that there's some loop there that's not allowing you to get close to that edge if you were going to go with your boat. If you take this edge out, there's still another path between the vertices on this side and that side, and the number of connected components stays the same. This is a little bit of hand-waving proof. You should make a case for when you're looking at a loop. If you're looking at a loop, R does not stay the same, and the number of regions always goes down by 1, and C does stay the same because taking a loop off does not change anything about the number of connected components of vertices. What's the net result? The net result, if R goes down by 1 and C stays the same, M goes down by 1. And now see what happened altogether. V had no effect, and the effect of E was that M went up by 1, and the combined effect of R and C was that M went down by 1. So the net result is that nothing, that M stayed the same. And so this completes the proof. So we proved that when you take an edge out, M does not change. And if you keep taking edges out, eventually you'll get to a squiggle with no edges. And we proved that for that squiggle, M is 1, and so it must have been 1 all along. Recap, well, we proved that for a general planar graph, v minus e plus r minus c equals 1. Here, c is the number of connected components of the graph. And we, in fact, proved that this is true even if you throw in some loops without vertices. If you do that, then c is not the number of connected components of the graph, but the number of connected components of the vertices. And the corollary of that is that if you have a connected general planar graph, then v minus e plus r equals 2. And this is, among other things, true for tilings of a sphere. I have a whole video on tilings of a sphere where I use v minus e plus r equals 2 to prove how you can tile a soccer ball. I have a previous video on tilings of soccer balls and planar graphs. This one was about Euler's formula. The next one is on which graphs are planar, where we use Euler's formula to come up with the necessary condition for planar graphs, and graphs on other surfaces is a subject of yet another video. Subscribe and like my videos if you like them, and if you want to be subjected to more videos like this, keep hydrated at all times, and I will see you at the next lecture.